Welcome to example 2 of my KVL KCL examples. I apologize, I would have put this in the previous video, but I was cut short because my camera decided to die. So I'll just do it now. Okay, so example 2, we're given this circuit, and we're asked to calculate number 1. Calculate VZ if VI equals 13 volts. So if we have a look at the circuit, we can see we have some loops. Over here we're given a current there and a current there, or we're not given, but we're told that there's a current there, so we're probably going to use that, and there's another current source there that we're given. But we're first asked to work out VZ if VI equals 13 volts, and these two parts of the circuit are essentially separate because they're only connected by the ground at the bottom. They're not connected at the top at all. So how are we going to calculate VZ? Well, if we were to apply KCL, which is the fact that the sum of all the currents in a node are equal to 0, that wouldn't yield much because we don't have any currents within this part of the circuit. What would be much more viable, because it's a small loop, is to apply KVL, but we will still need current, and you'll see now why. So if I draw my loop like that, if we apply KVL here, well, we only have a resistance there, so we're going to say V equals IR, because KVL is the sum of all the voltages in the loop. Voltages loop equal to 0. So we have to write that as some sort of voltage. So the voltage over there would then be 5 times whatever the current is, but we don't have the current, so we can define it as I. So I'm going to define it as I. So now we apply KVL. So we say it is minus VI, because we're approaching the source from the negative side, plus 5 times I, which we just said from V equals IR, and that applies to all these resistors. So you can say plus 6I plus 10I equals 0. And you'll see now why I wrote 6I and not VZ in place here. So we know VI from the question is 13 volts. So minus 13 plus 5I plus 6I plus 10I equals 0. So what I can do now is I can take this 13 over because it's not dependent on I. So that would become 13 on this side. And if we add these up, then we get 21I equals 13. Therefore, I equals 13 over 21 amperes, or 0.619 amperes. Let's just rewrite that nicely. Okay, so now we have the current in this loop. So what does this mean? This means we want VZ, and we have I and we have R, so we can calculate V from V equals IR. So we know the current in this loop is 0.619 times the resistance of 6 ohms, and that gives us 3.714 volts for VZ. Okay, so now we look at part 2 of the question. Part 2 says calculate IF if VZ is 20 volts. Okay, so IF is the current over here. So we're given VZ, which is the voltage we just worked out, but they give it to us this time. So we have to work out this current that comes out of this voltage controlled current source, because it's controlled by the voltage VZ. So the current out of there would therefore be, just do it in a different color, 0.2 times 20, which gives us 4 amperes. So we write that here so we don't use that 0.2 VC again, because we have a value. So okay, so now we say, how can we calculate the current IF? Well, we know that the current there is IF and the current here is 4 amperes, so it implies that we can have to do something to do with KCL, but we don't have the current there. We can say, okay, here's 10 ohms of resistance, and here's 40 ohms of resistance, and if the current through there is IF at 10 ohms, then surely the current through here would be 4 times less because there's 4 times more resistance. Let me say that again. Because there's a current flowing like this and like this here, the current through there would be 4 times more than the current through there because there's 4 times more resistance here. So therefore we just define the current through here as a quarter of IF. Because there's 4 times more resistance, a quarter of the current would flow through here in comparison to there. So now we can apply KCL because all our currents are defined. So we start here. So that would be, I'm going to take what goes out to be positive and what goes into the node as negative. As long as it all sums to 0, it does not matter. So IF plus 4 amperes plus a quarter IF. Oh, and we're using this node because we want to solve for IF, and doing anything here is not going to help us solve for IF. So we're just going to use this part of the circuit since they are virtually independent. And the sum of all the currents is equal to 0 out of this node, into and out of this node. So now I'm just going to add all the IFs. So that's 4 over 4 IF. So 4 plus 1 is 5 over 4 IF, which is equal to, if I take that 4 over minus 4, therefore IF, if I multiply up by 4 over 5, is minus 16 over 5 amperes. That is also the same as minus 3.2 amperes. And that is example 2.